Okay, so I just want to remind you that just a moment. In between more or less 2:30 until 3, please write down your name on the message section so that more or less 3:15, I will check your attendance. So without further, how can I say, reminder about that. So please remember. Okay. So we will now continue with the chapter 1 regarding the additive manufacturing technologies course. And we stop it more or less on the slide, let's say, the ninth slide. And let me show you where the slide here. Check. Okay. So let me open in full screen. So I just want to remind you that the general AM process basically contains let me say 8 steps. So the process need to go through one step which can turn the CAD model into the physical object. So generally speaking, 8 steps include, for example, the CAD computer-aided design. So you can use several kind of CAD softwares like Inventor, SolidWorks, or CATIA, or even you use the reverse engineering approach in order to scan the part in the case that this is too complex in order to model. We are using Inventor, let's say. You can use reverse engineering, like you computational tomography in order to scan layer by layer. So you have the point cloud, and then you use the correct appropriate software in order to reconstruct the cloud with the motor, with the motors, and you use the motor as the normal CAD motor that you construct by using, let's say, SolidWorks, for example. And once you have the CAD motor in the form of solid CAD motor, you need to convert into the STL form. The STL form, as I already mentioned to you that last time, that is actually the faces model or the surface model, which composed of many, for example, triangular elements. And this is necessary to guarantee that the CAD model is waterproof. In other words, there's no hole on the surface of the STL model. And if there is any defects detected by the software, and then you need to repair, you need to modify the model so that, yes, the waterproof properties need to be maintained. And once you have the STL model, and this model need to be set up in the software, for example, the NetFab, this one of the softwares that can be used to prepare the model before printing out this model to the physical object. You use such kind of software. Materialize is also powerful software in order to prepare the model. You orientate the model with respect to the building plate. You add the support structure and others. You arrange the model so that you have a kind of model which can be printed out at the same time, and so on and so on. And afterward, you need to transfer the STL file to the machine or the 3D printing system in order to print out the part or the model. The machine setup is also necessary. Yeah, for sure. You need to calibrate the machines. You need to import all the required parameters for the printing process, and then the build can be performed. And once the build has been completed, and then you remove the motor. You need to remove the motor. Actually now the motor is the physical one. It's no longer the digital model, but we print out the parts, which is the physical object, and you remove the object. But there is some complex steps regarding the sixth and the seventh step, because sometimes you need to perform the post process before you remove the part from the building chamber and from the building plate, and sometimes you just need to remove the part after building up and then perform some kind of post processing like cutting, for example, in order to ensure the dimensional tolerance of the part after the 3D printing process. And finally, you check the how can I say, to apply the part in the to examine the part with the real component, and to see whether it is functional well or not. Yes, to evaluate your part performance practically. And during the eighth step, you can also perform the virtual analysis by using, let's say, FEM package software in order to check the virtual performance of the part at the same time or before you print out the part and check your application practically. Yes, and some words regarding this process which have been highlighted on this slide. So you see here the process. You need to it includes let's say a step which are offering the chance in order to turn the CAD model into the physical object real. Simple product, in the case of simple products, and let's say the simple purpose. Yeah, you may remember that the initial purpose of using additive manufacturing is for rapid prototyping. So it's just for prototype the part for visualization. So this is the simple products and simple purpose. And with the development of technologies, it's now possible in order to print out the part and can be used practically. And also for the larger and complex product, and the process will be, how can I say, more complicated, and complicating, and they contain several stages. Sorry, the server asked me for the permission to join the room, and wherever I open the slide in full screen mode, and therefore it's difficult to check. Okay. Yeah. Here. Okay. So for the larger and complex products, the process may contain several stages and iterations within the development process, because sometimes you need to modify something and you find some step which can be improved, and then you perform several iterations, and for each iteration you can improve somehow the process. That's why it's called the product development process, because you are developing the product during that process. And yes, just to highlight again that most AM processes have 8 steps, and this can be divided into 3 different phases, as you can see in the middle of this slide. Just one thing, just one minor things, because I'm staying at home, and therefore, yeah, there may be some noise, unexpected noise that can be occur during the class. So just please ignore them. Okay, the first phase, which is highlighted by the light blue color. This is the design process. You started with the specifications. What about the requirement of the part? What about the functionality of the part? So that you need to design the part according to this specification to withstand a certain kind of load, for example, bending load, axial load. Yeah, whether this withstanding the distributed load and so on, whatever. Whether is work, it means been subjected to the humidity environment. So the environment which have high amount of let's say water gas, let's say humidity. And we have the and then we have to design the CAD model, yeah, by using the software. It can be the designing process in the computer-aided design software, starting from the sketch. You draw, for example, the circle, and then you extrude the circle so that you have the cylindrical shape. Let's say this is a 3D shape, very simple shape. And then you may be interested in performing the FE analysis to check whether the CAD whether your model can function well virtually or not. Just to be sure in advance that okay, the model can somehow work in the simulated condition. Simulated condition is not the real condition; it's just the simulated condition. You perform the FE analysis. You may have some idea about the FE analysis for some, but for the others who are not familiar with this process, so I would like to give you some basic information about the FE analysis. The process can be performed in, let's say, ANSYS ABAQUS. I'm not talking about the theory here, but generally speaking, you need to import the CAD model into the FE package software. You need to discretize the model, which means the divide the model into small elements. So the finite number of elements. And then you need to assign the element with a certain material or material properties, which means that you define that which material can be used in order to some kind of making the part. For example, if it's made of stainless steel, 7-4 precipitation hardening stainless steel, for example, let's say. So you know in advance about the mechanical properties of this steel. You assign for the material to this motor. Yes, and I would say the discretization process, which means the how can I say, the dividing process to the small elements is very important, because the smaller elements you could have, the more precision the result you could have afterward. But you know that when you refine the mesh, or you reduce the size of the elements, or you increase significantly the number of elements, and then the computational cost and time will be, how can I say, increased directly. Okay, how can I say, is increased in with the directly proportional relation. And yeah, just strictly, just strict. So please remember that. And once you have the discrete time model, and then you can define some kind of load, external load applied to the part. Constraint is meant to fix the model. For example, if you apply the load to this cell phone, and if you do not fix the phone in a certain position, and then when you apply the load, it will push, yeah, it will push the cell phone, so that it's been moved. And if you constrain, it means that you fix the position, you apply the load, and then yeah, this is the case. And once you have you have complete constraining the motor, you should define the regime. Regime means chế độ. For example, the linear elastic analysis, if the part works in the elastic region, or it may be the nonlinear analysis, it can be the motor analysis, it can be the buckling analysis, it can be the other type of analysis. It depends on the purpose of analysis of your analysis. Yes, and after the FE analysis, normally you can have some result like the stress strain distribution, the displacement of the motor. Yeah, you need to know about that so that we can check in advance that whether the stress occurs inside the motor smaller or larger than the allowable stress. If it's smaller, it's okay. But if it's larger, then it's not okay at all, and you have to modify your motor. Yes, so that to guarantee that if the part just work in the elastic region, and the stress must be smaller than the allowable stress. And the same thing you must do with the displacement, because during the class on Tuesday, I have mentioned to you about the shaft and the gear example on the shaft. And if you have the high deflection of the shaft, and then these gears can be blocked inside the machine. So, yes, so if you have the deflection or the strain or the deformation larger than the allowable values, and then yeah, you have to redesign your motor so that you put on the result. How can I say? You modify in order to have the results uh, falling in the allowable range. Let's say of stress, of strain, yeah, and displacement as well. That's why you have some kind of iteration here. So, vòng lặp is run from time to time so that you can have the better motor than the original, let's say. So once the model is satisfied with, let's say, the specification, based on your experience, you feel that okay, the model is fine, and then you can convert the solid motor into the SDO file. In other words, is the conversion process turning the solid CAD model into the physics model. It will be followed by the slicer, so it means that cut the model into finite number of slices. Yes, and each slide will define the contour on the boundary, and within the boundary, the how can I say, 3D printing system will, how can I say, scan through the area restricted by the contour, and the materials will be deposited to this area for X slice. And G code just code for controlling the movement in the CNC system, but okay, let's keep that thing because not the one that you may interested in now. It's not the one. And then once you have the slice, you have the model which have been sliced, and you can print out the model layer by layer until you build up the whole part. Yes, additively. Yeah. Okay, and the third phase is the some kind of testing phase, but you know check the performance of a part in the real application. So once we have the object, we have to test in order to verify the motor. Verify is something like to check between the performance of the real part and the part which you have performed the FE analysis to inspect the performance virtually in the simulate condition. It means that this is the FE analysis. The testing here is just the real experiments in order to see whether the part can work well. This can withstand, for example, 20,000 cycles, working cycles, because before it fails, or it can still working, can still work, can still work. So it is okay, then it's passed. Otherwise, it fails, and then you have to come back to the design stage or you can assign the model with different materials, the stronger materials, yeah, in order to improve the properties, improve the performance of the part. Yeah, this is normally the product development process, and it can also be used uh, um, for developing the part that can be fabricated by the additive manufacturing process. Yes. And this is an example. At the bottom of this slide, you can see an example of 3D printed GE General Electric aircraft engine bracket. Is the bracket. The original design is something highlighted in black here. This is a solid motor, and by using the FE analysis software, you can easily point out the stress or the strain distribution within the volume of the part. And for sure, there are certain area within this volume have very low stress. And that's the reason of performing the structural optimization. Why? Because the area or the small volumes which have low stress should not be there, because we are wasting materials. The high stress area need to be supported, but the low stress area should not be present, because if material there is placed almost nothing. Yeah, but the red area here is the area withstanding high stress and need to be supported, and the reason need to be kept. But the other reason in blue, for example, can be reduced, because it's low stress area. In order to reduce the weight of the part, why we can try to maintain the compatible performance of the part with respect to the original structures. And by performing the optimization process, for example, the topology optimization, uh, so is somehow linked with the FE analysis, but there is a correlation between the stress distribution and the density distribution among these elements. So the higher stress, the higher the relative density of the elements are, and lower stress correspond to the low density elements, and the low density element can be eliminated. Yes, just by using the software, you can select the low stress elements or the low density elements, uh, and to build up the so-called optimized model. And the second figure show here the optimized model after running the FE analysis. Yeah, and you can check with the allowable stress strains. You can perform the fatigue test to see how many cycles that the new component can withstand before it damage, or before the initial crack occurs uh, on the most critical surface of the part. Because the crack tend to occur there firstly. Yeah. And once the motor is checked and you see that okay, it can perform well in the virtual condition, uh, in simulated condition, and then you can print out the part. Yeah, and print out the part. So you can print either in the form of the plastic material, just to show your boss, for example, just for visualization as the initial purpose of using AM, additive manufacturing, or you can directly print out the part in the form of metals to be able to subject the part in the real working condition in the airplane, in the aircraft. Yeah. Come on. What is it? Yeah, probably it is the next slide because I'm sorry. I just want to check that I'm showing you the okay, because I see the Google Meet is sharing a window here, so I'm sure that you are viewing the slide. So I just want to highlight on this slide that okay, the generate and process contains if step, so which has been shown on the left side of this slide, and I have already given you some ideas about the its step, and on the right side you can see a little bit more complex diagram or the flow chart showing you several approach in order to fabricate the real component, starting from the product idea to the real physical object. So when you design something, yeah, when you try to, sorry, server asked me for permission to attend the, oh, come on. Sorry for that. I have to check the Google Meet. I'm sorry, I forgot to share my screen. Really? Okay. Okay. Just want to check because yeah, it's normal. It's normal. Uh, it's due to the quality of the internet connection. So even in the in my circumstance, in my situation, I may also have some kind of problem during the lectures, during the class. So it's normal. It's normal. So don't worry. Okay. So now I continue to show you this slide. So here. So generally speaking, we start with the product idea. So you should have you must perform some kind of brainstorm in order to find an appropriate idea for designing a certain part. Of course, your customer or your boss will give you the requirements before you design the part. What about the working condition of the part? What about the load? Yeah, with the part need to be example with the other part. So you have some kind of geometric constraint. You have about the constraint associated with working condition, uh, the stress distribution, the maximum stress present inside the part, and so on. So, so that you can have some ideas about how to design the part. Yes, and the idea also can also come from the real parts. For example, you like you are an artist, you shape a part with clay. That's set. You shape the part with clay because the shape is quite random. It's quite how can I say? It's not the engineering shape, but that is the how can I say? Um, any shape you like, and maybe difficult in order to generate it by using the CAD software. So in that case, you can shape manually by hand, by clay, and then you use. You can see from here reverse engineering method. You scan, you scan the clay part, yeah, because you just need to define the shape at that time, just the shape. You create the part by clay, you shaping the part manually, and you use the 3D scanner, to scan the part, and then you have the point cloud. So you have the cloud containing a lot of points, yeah, and then you use the software in order to reconstruct the surface model, yes. And then you have some kind of several file formats like the step formats. And I have at least one time mentioned to you that the step file here is the solid model. Even here is the surface model, but you can convert into the solid model. IGES is also the solid model, but but to be honest, I do not know about the VDAFS formats. I haven't used this before. And and then you have a 3D CAD modeling. And please remember that 3D CAD modeling, in general, is referred to the to the solid model. You can also have the surface model. I'm sure that, but here we talk about we are talking about the solid model. Why? Because this is a volume model. I just want to highlight that in order to distinguish with the surface model. And after you have the volume or the 3D model, you can convert into the faces model or the surface model by implementing the triangular elements to the surface. Or you can also use the uh, polygonization. Yes, polygon is the hình đa giác, polygonization. So probably create a lot of elements having the shape of polygons. Yeah. So this is the process where you convert the solid model into the SDL model. Yeah, it's the faces model, and then you slice the model, and then you have the different contour data. So defining the boundary region that the material will be deposited to build up the part for each slice and then you have from here slide contour data. You more or less have the complete how can I say set up the printing model, and then you can perform the next step of building up the part. This means the additive fabrication process. And yes, before the final stage, you have the real component. You need to remove the part. You have to, for example, performing several post-processing steps, and then you have the final component, and it need to be checked. Yeah. Okay. So now I will let you have an opportunity to ask me a question about how can I say, the A step on the left side of this slide and the flowchart on the right side of the slides. So do you have any questions for this? Okay, no question. Okay, so let's say now is 12:30, and probably some may have lunch at the moment. Can have lunch at the moment. Whatever. Have a nice lunch. Okay. Just for fun, just for fun. So please do not leave the class and having lunch at the moment. Just for fun. Okay. Okay. Next slide. So this slide just the purpose is to provide you about the summary of the steps that you have mentioned to you on the two previous slides. So highlighted a little bit in detail about the 8 steps. So the CAD computer design, you have the 3D solid or the surface CAD model. Yes, but be careful when you prepare the surface CAD model, because you need to pay attention to the thickness of the CAD model, because it's not always possible to print out the model with very thin thickness. No, it's not possible. There is a restriction, and for certain material, you have to pay attention to the minimum one thickness that the technique can be used to print out the model. Okay, so usually the 3D CAD model or the surface CAD model can be created by the CAD software, or can be used can be generated by using the let's say the 3D scanning method. So it especially apply to the case of the artist motor. Yes. SDL conversion is the second step. Yeah. And why we have this? Because the CAD model cannot be used directly to the AM printer. And then you need to convert the CAD model into the SDL model, which can be widely accepted by the majority of AM machines. And just to remind you about the SDL file having the information of the external surface, and these surface need to be closed. So without the presence of the hole, or it need to be waterproof. So, so once you have the SDL file, and then the software can help you to calculate the slice, which means that cut the motor, the SDL motor into different slices. Yes. Yes. Another thing, just to remind, because I usually remind my students about the working schedule each day. So again, similar to the first class at this course, we let's say run the class for 50 minutes, and afterward we have 10 minutes break, and then we resume the class. So at more or less 10 to 1, we stop. We continue at 1, and then 10 to 2, stop, and then continue at 2. And afterward, we can finish the class more or less in part 3. And this is also the time for me to check your attendance. Yeah. Where am I? File transfer to machines. Yes. And once you have the SDL conversion, and I would like to highlight here that the SDL conversion can be directly performed with your CAD software. So for example, by using Inventor, you can convert into the step file, or you can use the extension of the file is ITP, as ITP probably. I'm not sure. But if you use the default file of Inventor, you can also convert directly by using Inventor to SDL files. So just to select the quality of the file. So the smaller the elements are, and the file is large. The larger the file is, So, and sometimes if the file is too large, and then that maybe it's a challenge for the software which can use for controlling machine, to run this kind of file. Yeah. And and you need to export the file. Yes, and import this file into the AM machines. And for each AM machine, there will be a software which can be used to control that kind of machines. And with this software, you can manipulating the file to correct the size, position, and orientation of the beam. This can be handled by the software, which can be used to control the machines. So directly embedded in the machines, or you can also use the software as I mentioned, called Autodesk NetFab, or the Materialize. You can check online. NetFab, NETFABB. NETFABB is the Autodesk NetFab, which used to prepare the motor for the additive manufacturing process. So, and by using this software, you can also prepare the motor, regarding the side correction, position, and orientation for the building. Yeah, side, yes, because when you draw the model can have the real dimensions of the part. Yeah, the real dimension. For example, let's say 20 centimeters. But if you want to scale down, okay, I just want to print the part, for example, in the 10 centimeter length. So the model needs to be scaled down. And then this can be done by the software. The positions, this means the position of the part with respect to the building plate, because this above this is above building plate for 5 millimeters or 5 centimeters, let's say, for example, just for fun. But you can select the position of the part with respect to the building plate. And the other important parameters is the orientation of the part with respect to the building plate. Yeah, this is important because it affects the quality of the part after the 3D printing process. You know, you probably know that the additive manufacturing process tend to be used in order to fabricate the part with the anisotropic properties. Anisotropic properties, which mean the property of the part in different directions will be different. So this is unwanted, I would say, because we want the material having the isotropic properties, which mean properties in different direction will be the same or similar. The same will be the ideal case, the best case. But similar is also acceptable in some situations. And yes, and the orientation is quite important because we tend to print out the part so that the direction, which direction withstanding the highest load will be given favorable. Did you get my point? The thing is that we want to orientate the part for the printing process so that direction which can withstand the highest load will be used for withstanding such kind of load. Ok, in Vietnamese có nghĩa là như thế này các bạn. Đó là khi mà chúng ta in vật bằng cái phương pháp in 3D, Additive Manufacturing Technology này, thì cái tính chất của vật liệu, bởi vì nó là từng lớp nó tạo, nó xếp chồng lên nhau và nó liên kết với nhau như quá trình hàn từng lớp vật liệu một. Tôi lấy ví dụ nếu là vật liệu kim loại. Thế thì cái vấn đề ở đây là cái tính chất của cái vật liệu nó sẽ là tính anisotropic. Anisotropic là tính chất theo các phương khác nhau thì khác nhau. Cái này người ta không mong muốn. Chúng ta mong muốn tính chất nó phải homogeneous, có nghĩa là tính đồng đều, và tính nó phải là isotropic, có nghĩa là tính chất theo các phương khác nhau thì nó phải gần giống nhau hoặc là giống nhau là tốt nhất, đúng không ạ? Thì khả năng chịu lực nó mới tốt được. Tính chất theo các phương khác nhau mà khác nhau thì nó rất là nguy hiểm. Cho nên là cái orientation, cái định hướng của cái model ấy trong quá trình in nó rất là quan trọng, bởi vì nó ảnh hưởng đến cái tính chất của vật liệu sau quá trình in. Và người ta xu hướng là chọn cái phương in làm sao cho mà cái phương nào ấy mà nó có khả năng chịu được cái lực tối đa thì dùng cái phương đó, đúng không ạ, để mà tạo ra chi tiết, và cái chi tiết đó nó sẽ chịu cái lực đúng theo phương đó là maximum. Thì đó là cái orientation. Và cái orientation nó cũng rất quan trọng bởi vì nó ảnh hưởng tới cái support structure. Support structure có nghĩa là những cái cấu trúc đi kèm với cả cái mẫu in để mà chống đỡ cái mẫu in của chúng ta trong quá trình in. Bởi vì các bạn biết là in về mặt nguyên tắc là nó phải tạo ra, nếu mà in về kim loại lỏng, in kim loại chẳng hạn, thì rõ ràng chúng ta phải melt cái kim loại đó, có nghĩa là làm cho nó nóng chảy nó ra. Thế thì nếu mà nóng chảy nó ra thì nó sẽ phải chảy, nó sẽ phải nhỏ xuống thành từng cái droplet, từng cái giọt một. Cho nên là nếu như không có support structure, đúng không ạ, thì cái droplet nó cứ nhỏ xuống bởi vì có gravity, có trọng lực. Thế cho nên là chúng ta cần phải có support structure ở đó. Thế thì có orientation này nó cũng quyết định đến cái lượng support structure mà các bạn cần để hỗ trợ cái cấu trúc trong quá trình in, và cái cấu trúc hỗ trợ đấy nó cũng góp phần là tản nhiệt, heat dissipation cho cái vật của các bạn, thì nó giảm được cái chênh lệch nhiệt độ giữa bề mặt và tâm của chi tiết, hoặc là trên hoặc dưới của chi tiết, thì nó sẽ giảm được cái trạng thái ứng suất dư sinh ra do thermal gradient, có nghĩa là sự chênh lệch nhiệt độ. Thì grand orientation này nó rất là quan trọng, và thường là cái software của chúng ta sẽ cho phép chúng ta lựa chọn cái orientation căn cứ vào ba cái tiêu chí. Tiêu chí thứ nhất đó là cái building time, có nghĩa là cái thời gian các bạn in. Nếu như các bạn muốn ưu tiên cái thời gian cái building time nó ngắn thôi thì chi tiết nó sẽ sản xuất ra nhanh hơn, đúng không ạ? Nhưng mà thường thì khi mà các bạn quay ngang cái chi tiết cho nó nằm song song với cả cái building plate chẳng hạn, thì cái thời gian thường nó sẽ là ngắn nhất. Tuy nhiên là tất cả các cái mặt của nó sẽ đều phải có support structure so với cái bên dưới, so với cả cái building plate, và như vậy thì cái lượng support structure sẽ tăng lên. Nó ngoài cái vấn đề hao phí vật liệu thì các bạn sẽ phải tăng cái mức độ gia công xử lý sau quá trình in, tăng các cái bước gia công cho cái quá trình post processing ấy, vì chúng ta phải cắt đi nhiều các cái support structure. Và các bạn biết là thêm một cái bước gia công thì thêm tiền, rõ ràng giảm được các bước gia công thì chúng ta sẽ tối ưu hóa cái vấn đề chi phí để sản xuất ra chi tiết. Đó. Machine setup. This is the setup prior to the building process. So you have to consider about the material constraint, energy source. Material constraint it can be the minimum layer thickness that the machine system can deposit. So usually how can I say, for metallic materials like steel, stainless steel, aluminum materials, so the minimum thickness of the layer materials can be 20 microns, 20 micromet. Yeah, so far I remember 20-40 microns is the minimum thickness of the deposit material that the machine can coat. Coating process phủ lên, cứ mỗi một lớp phủ đấy là khoảng minimum là 20 micromet, vì chúng ta rất là khó để mà phủ lên cái lớp vật liệu mà nó có bề dày của cái lớp đó nhỏ hơn 20 micromet, bởi vì cái tính chính xác của cái việc phủ đó đúng không ạ, nó có rất nhiều vấn đề. Energy sources can be the laser source, can be the plasma source, can be the electron beam source for melting metallic materials, because this is a high energy source. You need to melt the metal. But for the printing out the plastic material, and then the heat source does not need the high energies comparing to the case of melting metals. Yeah, for sure. Layer thickness, yeah, timing, yes, which means that you need to define the printing parameters. Yes, define the printing parameters, and I would say that unless you refer to the set of parameters which have already been developed by the printer suppliers, which mean the printer manufacturers, you will have challenge if you want to play with the printing parameters, because you have more or less 180 more than 180, so 180 printing parameters, and the parameters can have a lot of values in a certain range, and if you combine them together, there's many sets of printing parameters you could have, but there are few sets that can give you the best quality parts, let's say, after the 3D printing. So this I mean that if you refer to the optimized sets of these parameters suggested by the printer manufacturers, this will be okay. But you try to play with these parameters is a real obstacle, really a big challenge. It's not easy. It's a matter of cost and time, because you need to perform many experiments, many before many simulation processes in order to point out an let's say a suitable set of printing parameters or an appropriate or a proper uh, printing parameters set. So it's quite difficult. And normally, this is required to keep them confidentially because it's a matter of cost and time. Uh, Build, yeah, this is an automated process because once you set up the machines, once you define the model and import into the 3D printer, push the button, and then the process is automatically performed. Yes. And just wait for 24 hours or more than that, or maybe less than that, and you could have the part, the printed part, but not the final part, the printed parts, or the printed part. Yeah. Okay. I stop at the building process, and we can have a 10-minute break, and we can continue at 1.